Hello and welcome to video series, very exciting video series on vectorization, loopless coding in Python for data science. We can by the way replace this term loopless with efficient maybe. So efficient coding in Python for data science. But all that has to deal with vectorization. So this video series basically consists of three parts. In this part one, we will basically discuss what vectorization is, and we will see a couple of examples to actually motivate the viewer to actually start coding using a vectorized fashion, particularly if you're working with in data science or deep learning or machine learning and stuff like so. In part 2 and 3, we will see some concrete examples from data science and computer vision that at the first glance may look very difficult to code them as without loops, but then we will see the tricks to actually convert them into a vectorized fashion. So let's dive in, but first and foremost, what is vectorization? Well, before discussing vectorization, let me discuss maybe one key difference between the programming languages, because this vectorization is relevant to the coding and the coding is done in programming languages. So let me discuss some of the differences in or let me differentiate programming languages with respect to one characteristic, that whether the programming languages whether a programming language is interpreted or compiled. It turns out that the programming languages that are compiled or compiled programming languages, they actually are much more faster. And the reason is the code is compiled and all the analysis is done pre-hand, just at the compile time. That's a whole compilation layer in that. And all the analysis is done before actually running the code directly on. In terms of interpreted languages, each statement is analyzed once it is actually being executed, and sometimes it takes a lot of time if you have a lot of statements in your program. The examples of compiled languages, the very classical example is C language, and interpreted languages, for example, Python is interpreted, and there are several other interpreted languages. Apart from Python, there are other a lot of interpreted languages as well. But for example, R is interpreted, PHP is interpreted, and there are several others. But we mostly interested, because we are interested in Python. In this particular video series, we are focusing on Python. There are a couple of reasons why Python should be focused for data science that I have already explained in my other tutorials on data science. But let's focus on Python, and unfortunately Python is interpreted language, which means if your program has a lot of statements, then the Python will become slow as compared to obviously a compiled language like C. So what happens when we write a loop, for example, in Python for I in range, let's say 10,000, and here we do something, let's say print I. What happens normally is, in this code snippet, this is a statement that actually is generated, that actually is executed 10,000 times, and every time it executes, in theory basically it is interpreted, which takes time. So in loop, actually you have a lot of statements that are unraveled and interpreted, although the code written in a few statements, but when you unravel the loop, it becomes a lot of statements. And in interpreted languages, if your code has a lot of statements, a lot of instructions to be executed, to be interpreted, it will become slow as compared to a compiled language like C. So the idea of vectorization is, very loosely, the idea of vectorization is the following: avoid explicit loops whenever possible. So the idea here is to come up with a programming, come up with a coding or equivalent coding to achieve the solution of a particular task, and avoid to write loops yourself. Avoid explicit loops. That may bring you towards recursion. So for example, you may think, okay, that's the loop that is making all the trouble. Why don't I write my function recursively, because then there will be no loop. Well, the whole point, as we saw in previous slide as well, the whole point is to reduce the number of statements that actually are interpreted in an interpreted language. So whether you use recursion or loop, the idea is the same. So should we define vectorization as avoiding just loops? Well, technically no. There are multiple aspects, but that is one kind of definition that people come up with when they say vectorization, so avoid explicit loops. But there is a more concrete way of looking at the vectorization. That is, basically, if you're working on arrays, large data sets, then you may apply loops to process those arrays. And vectorization is a way to transform the loops to array expressions. So process the large arrays, process very large arrays, very large data sets, and try to process them without loops. Well, you might be thinking, if we have to process arrays without loops, then what should we do? I will say, okay, use some built-in functions to do that. You might be thinking now, okay, those built-in functions, they themselves have loops. They have loops. So essentially we have an avoid loops. Well, the crux of this idea is the following. There are libraries in Python that has built-in structures that are much faster than the code that you will be writing in loops. For example, one such library is NumPy, and that is extremely faster. For example, if you have two arrays and you want to compute their dot product or any other function, let's take an example of dot product. Calling a built-in function dot product in NumPy or using an operator overloaded in NumPy will be much faster than applying a loop. Now you might be thinking what NumPy has done inside, because eventually it has applied loop itself. There is no other way. Well, the NumPy basic code is all written in C rather than Python. So inside NumPy, a lot of C code is there, the pre-compiled code is there, which is much faster. So when it comes to a compiled language, then there is no problem of writing loops or not loops, because compiled language is much more faster. So the library like NumPy has a lot of compiled code, and it has a complete compiled layer inside that when you call built-in functions from NumPy, it will call the loops. It has its loops, but those loops are written in a compiled language. So there is a compiled layer that makes these functions much faster if your data set grows more and more. And if you write loops explicitly yourself, then you would be avoiding, actually avoiding the efficiency that is offered by NumPy. Now let's see how, for example, if you're working in data science, and I'm here explaining that this is the NumPy that has this kind of structure. If you use built-in functions, transform your code into products, operators in NumPy, that will be much more faster than writing the loops. You might be thinking that you have to work in a lot of packages. This is just one package. Then here is a good news. NumPy actually is the basis of a lot of packages. For example, Pandas is built on top of that. Matplotlib is built on top of that. Matplotlib. Scikit-learn built on top of that. TensorFlow built on top of that. Almost any data science package that you can think about, it builds on top of NumPy, which means it is enjoying all the vectorization, all the speedups that are available in NumPy. So to sum up, vectorization basically in data science particularly, is to come up with a code that avoid loops and uses array expressions or built-in functions, particularly in this particular context, maybe in NumPy. So let's go to Python and actually test what I'm saying, that writing loops and achieving the same kind of stuff using a vectorized code, how difference that it makes. Let's test a couple of examples and let's actually write code to test vectorization in Python. Let's test its speed just on a couple of examples. So let's go to Jupyter and write some code. All we need is for this particular test, all we need is NumPy, for example. So import. Let me increase the size of this. Yeah, maybe 200. Is that fine? I guess. Import NumPy. Maybe I should hide that. Import NumPy as NP. So next what we do is we generate, let's say, two arrays. Let's say X is np.random.rand, and let's say we have an array of size, let's say maybe 100,000. That's an array. Let's generate another array, np.random.rand with size length of X. So these are our two arrays. Just we are going to actually implement dot product on these. So let's implement a dot product using a for loop. So and we will see the speed of that, and then we will see how can we use the vectorized, how can we actually vectorize this implementation, and what will be the speed up. So define f underscore dot. Let's say it accepts X and Y. And what this function does is the following. So that's the naive implementation that I'm going to do. So S is 0 in the beginning, which is the result of the dot product, the sum of products. For I in range length of X, what we really do is we actually say, okay, S plus equals to Xi asterisk yi. So that's our that's the dot product, which means just multiply the corresponding entries and then sum the products. So return S. So that's our function. And let's write a vectorized code for it. So define f vectorized dot xy. We can use a built-in dot function from NumPy, or we can just use the operators as long as these X and Y are NumPy arrays, no problem. So S is, we can actually just return X pointwise multiplication with Y, and whatever the result is, dot sum. So that's the vectorized code. Just pointwise multiply them. This static operator just pointwise multiplies all of these things, and then you just add a sum there, no problem. So that's the vectorized code, and let's test the difference in time of both of these. So let's just use this time it function, time it f dot. It will give us the time that is taken by f dot, and this time it will call this f dot multiple times to actually give you a stable time with variance and standard deviation and means and all that stuff. So it will take some time to run this code. So that is this static there, which means it will take some time. The arrays are a little bit bigger. That's 10,000. Actually, that's 100,000. So the total time it required, basically, it actually calls this 7 times, and so 7 different calls, and this is the mean. On average, this function took 171 microseconds, and this is the standard deviation or the variation in different runs. And that was a non-vectorized code. Now let's test our vectorized code for that. So time it f vector dot x and y. See, these are exactly the same arrays, so the same problem, same result will be there, but maybe there will be a difference in time. So it may take a couple of, actually more than a couple of seconds, because it does multiple runs. So now you can see the time it took is basically 141 microseconds with this standard deviation. And that's particularly, so now you can see this difference, 171 and 141. That's a difference between the vectorized code and the non-vectorized code, which is a huge difference if the array actually becomes larger and larger. So let's do a couple of more examples. Let's, for example, write a code that accepts two tensors. A tensor is just a multidimensional matrix with more than 2 dimensions, basically. Let's write a code that accepts the 2 tensors and actually returns the Frobenius norm of their difference, or for example, pointwise subtraction, and then squares, and then sum. So sometimes consider the flattened variance of 2 tensors as vectors, so then just return the square difference. So let's write first let's define x as np.random.rand, and let's say we have a tensor of size, let's say 10, 10, 10, maybe 20. So that might be a tensor. So now if you see the shape of x, it is actually 10 by 10 by 10 by 20. So which means the total number of elements are around 2000. Maybe yeah. So 1000 and 2000. Maybe we can make some of these as larger like this, and some of these as further larger like this. And now you have this shape. Now let's define y also with the same dimensions. Y equals np.random.rand and 10.30.1000.20. And let's say we want to compute the square difference between corresponding entries, and then we want to add all these square differences. One naive implementation is f underscore define f underscore least square square sum square differences and sum. Let's say SDS, square differences and sum. It accepts x and y, and we know that these are 4 dimensions, so let's write like this. For I in range x dot shape 0, then for j in range x dot shape 1, then for k in range x dot shape 2, and then we have obviously we have 4 nested loops because that's a 4-dimensional matrix, or sometimes called a tensor, for ijkl l in range x dot shape, and that's 3. And now what we do, we really want to find out the square sum. So let's say s is 0 in the start, and then we have this here, s plus equals to xi j k l minus y I j k and l, and we need this to be squared. So let's do that, and that's the squared sum. And then we really need to return this result, return s, and that's our function. And now let's write the vectorized version of the same function. Define f vectorized sum of square differences sum, and it accepts x and y as tensors. So there are several ways of doing this. I really want to write a very kind of for example, I mean, let me write that in one line, just one line. Maybe you can call it as one-liner. Return x dot flatten, which means make it a vector, minus y dot flatten, make this as a vector. That's one way of doing the same thing. Then take their squares, element-wise square, and then just write np.sum, and that's one way of doing the same stuff. So that's one way. So computing the sum, that's one way of computing the sum. Another way, that's one way. Another way of writing just that, the same statement, right, like in the is the following. So x minus y, element wise, then squares, and then we can call np.sum. So let me call np.sum, np.sum. That's it. That's another way, and there are a couple of other ways as well. So let me focus on the first way, and let me focus on the very first way, although both of these are vectorized variants. And then we return the s, and let's see how much time does it take on x and y. So time it f sds x and y. Let's see how much time does it take on these tensors to actually compute this number. So it is basically 1 second. On average, it takes 1.08 seconds, and it actually does 7 runs for that. Now let's compare this with our vectorized variant, f vec x sds x and y. And let's see how much time does this actually takes. You can now see a huge difference. You have the non-vectorized variant actually takes 1 second, and the vectorized variant of the same problem actually takes just 18 milliseconds, which is really small than this. And as the size of the matrices or the tensors, it grow larger and larger, you will see this reduction more prominent. And by the way, if I just change this line with this one, because the running time will not change significantly, because the two are exactly the same variants, exactly the same. So let's see. So the time might be different, but it will be closer to 18 milliseconds, around near it. Oh, it's much better than that. Maybe it's due to, maybe I run it again and I get different than that. But the point of the story is the vectorized variant one, the vectorized code is much smarter to write, much elegant, much more readable, and it is much more faster. And it builds on top of the compile layer, particularly in Python NumPy. So do not write these loops. And do not think that the built-in functions, they actually have these loops, so why don't I write these loops? Actually, those loops that the NumPy actually using inside in the built-in functions or in these operators, they actually use the compiled layer in C rather than the interpreted layer in Python. So yeah, I mean, use vectorization wherever possible. So I hope you have liked this video. In the next part of this video series, we are actually going to talk about finding out k nearest neighbors of a particular point. Not a particular point, let's say we have 100 points, and we want to find out the, let's say, 5 top neighbors with respect to certain, let's say, Euclidean distance of every point. It looks like that this problem that we are going to cover in the next video, it looks like it may be harder to actually make this problem loopless, because one way or the other there might be a loop, explicit loop on there. But we will see fancy kind of indexing in NumPy. that actually achieves that problem very in just a few lines of codes and very efficiently. So hope to see you in the next part of this video series.